Hello everyone. In this video we'll discuss about finding Fourier transform of the given signals. Now, the only thing that comes in mind is whatever the examples are given, we have to solve this using the properties. So based on that, let us come across the first example, which is given x of t as exponential u of t minus 1. Now here, if you observe carefully, our input signal is shifted by 1 unit. Now whenever it is shifted by 1 unit, definitely we have to use time shifting property, which simply says if x of t be any signal having its Fourier transform as x of j omega, then if it is shifted by certain amount of time, the same will replicate in the input output side, which is e raised to minus j omega t naught into x of j omega. Now in order to find Fourier transform of this signal, if you observe it carefully, this is e raised to minus 3t into u of t minus 1. I am considering let the function, I am treating it as x1 of t as e raised to minus 3t into u of t. Now we already discussed, we already solved an example on this as Fourier transform of e raised to minus 80 into u of t is equals to 1 upon a plus j omega. This example we already solved, you can check in the previous videos. Now based on that, I can write Fourier transform of this function becomes equals to 1 upon, instead of a, now this is 3 plus j omega. If it is there, we will now shift by time period as 1. Therefore I can write Fourier transform of e raised to minus 3t into u of t minus 1 becomes equals to, now we have to introduce exponential term with shifted version as 1. So here it becomes e raised to minus, we have a shifted version with time period t naught, so this becomes equals to 3 plus j omega, and the original transform is 1 upon 3 plus j omega, so this becomes divided by 3 plus j omega. So this is the answer of first question as Fourier transform using time shifting property. Now let us consider the second example where the input signal is multiplied by certain duration as t. Now whenever it is multiplied with certain duration of time as t, we have to go for a property that is called as differentiation property. That property we have known Fourier transform tx of t will be equals to j into d by d omega. This is d by d omega x of j omega. This property is basically known as differentiation in frequency domain property that we already seen in the previous video. Now in order to fetch Fourier transform of this signal, we have to determine if x of t is any signal, its Fourier transform will be x of j omega. Similarly, we have to find Fourier transform of t exponential into u of t. So here we will first find Fourier transform of e raised to 2t into u of t. It is as good as e raised to minus 80 into u of t. So this becomes 1 upon 2 plus j omega. Now when I multiply input signal with t, its Fourier transform becomes differentiation with respect to omega. Therefore we will write the next step as Fourier transform of t e raised to minus 2t into u of t becomes equals to j into d by d omega of 1 upon 2 plus j omega. Now let us differentiate this. So for that case we have to use a formula that is called as u by v rule, that simply says j I am keeping as it is, 2 plus j omega into differentiation of 1 is definitely 0 minus 1 into differentiation of this term, 2 ka differentiation 0 and j omegas will be only j divided by v square, that is 2 plus j omega whole square. This is u by v rule. Now if I simplify, this is going to be 0, this is minus j into j will be minus j square, and that will be 1. So our answer becomes equals to 1 divided by 2 plus j omega whole square. So this will be Fourier transform of the given function. This is by using differentiation in frequency domain property. Now let us come across the next and very important type of example, that is, you can read the statement. Here it is given, determine the output response of system whose h of t is given, that is nothing but impulse response is given and input is given, and they have asked you where to use Fourier transform property. Now here two terms are given and we have to determine an output term, that is going to be y of t. Now in order to solve such kind of examples, we have to deal with input and output. Now if it is an input and output, we have one property that is called as convolution property, that is convolution in time domain property, that simply says convolution in time is equals to multiplication in frequency domain. That I can write, if I multiply these two signals with each other, that is x of t convolved with h of t, it will be equals to x of j omega into h of j omega. If it is there, I can just concentrate on this term h of j omega. This simply indicates transfer function or gain of the system or transfer function of the system, and we know that transfer function of any system, I am writing in terms of frequency component, it will be the ratio of output by input. We know this system, output by input. Even gain of the system will be equals to output upon input. So based on that, we can write y of j omega is equal to x of j omega multiplied with h of j omega. Now once you got y of j omega, we can find its inverse Fourier transform, and that becomes our output response of the system. So for that case, let us put those values. Fourier transform of input signal e raised to minus bt into u of t. Now friend, the same term arises here, only the changes we have b here. So I can write its Fourier transform as 1 upon b plus j omega. Similarly, the Fourier transform of h of t, which is e raised to minus at into u of t, which will be 1 upon a plus j omega. Now I will put all these values in the given equation so that our equation holds. Y of j omega is equals to, this is for x and this is for h, so I can write 1 upon a plus j omega into b plus j omega. Now in order to find y of t, here we should go for this simplification. Now this simplification we can do by using partial fraction expansion. So I am writing use partial fraction expansion. Now if I want to use this partial fraction expansion, I can split y of j omega as a plus j omega into b plus j omega, which I can write as a upon a plus j omega plus b upon b plus j omega. Now we have to simplify this and we have to find the values of a and b. Let us find those values. I am keeping it aside. Here it is. This simplification holds 1 upon a plus j into b plus j is equal to cross multiplication becomes a into b plus j omega plus b into a plus j omega upon multiplication as it is a plus j into b plus j. Now this term will get cancelled and we are left with this one. Now in order to find a, we have to treat b as 0, so we will write to find a what we can do, we can put this a or simply j omega as minus a. Now why minus a? Because plus a minus a will be 0 and definitely this product term will be 0. Therefore this equation holds. 1 is equals to a into b as it is. Instead of j omega we have minus a and this term is 0. Therefore we got the first constant term, a is equals to 1 upon b minus a. Similarly, in order to find b, we should make a term as 0. So we have to put j omega is equal to minus b. So we'll get 1 is equals to, this term will be 0. We are left with b into a minus b. Therefore second constant term will be 1 upon a minus b. Now once you got both these terms, we'll put them here. I can write y of j omega, this is equals to a is given as 1 upon b minus a divided by, we have a plus j omega, plus b we have 1 upon a minus b divided by b plus j omega. Now I am writing them in a proper way, so this becomes 1 upon b minus a into 1 upon a plus j omega. Similarly for this term, 1 upon a minus b into 1 upon b plus j omega. Now we can take inverse Fourier transform of y of j omega. Now for that case we should use the same correlation. We know that Fourier transform of e raised to minus at into u of t will be 1 upon a plus j omega. If it is there, we can recall it. Inverse Fourier transform of this function will be e raised to minus 8 into u of t. So we have these two sets of equation. So I can write, taking inverse Fourier transform. So y of j omega's inverse Fourier transform will get as y of t, which is equals to the first constant term as it is 1 upon b minus a into this inverse Fourier transform holds e raised to minus at into u of t, plus for this case here first constant term